Okay, starting this one off with a joke again. Why do you never touch a mathematician's pencil? And the answer comes from another joke. Why are mathematicians not afraid of constipation? And the answer to both of them, a mathematician knows that he can work anything out with a pencil. Okay, going into static frame mathematics, the main formula we're looking for is velocity equals the square root of the gravitational constant times the mass that the object is going around divided by the radius. Okay, the first thing I want to look at is the solar system and how they map this into a galaxy and how they used this equation to get galaxies. It is very simple. It's 0.998, and I just use a 1 kilogram for my whole system, and I used basic standard units. So I'm starting off with this number here. It is just a basic random number for this particular dimension of what I'm using. I'm scaling down a solar system. I'm scaling down a galaxy even more. And I'm getting just a standard number to start with. The first thing I did is I started adding up, because we have different center of masses, and later I'm going to add more masses here. And I've got this is the part going around, and it's going around this mass. The gravity that is affecting it, affecting the velocity of this to equal out, is this mass right here. So if I put different masses in here, then I have to add these velocities together. And I did so and thought about it and said, hey, wait a minute, I better check the math on that. And I'm sort of glad that I did, because what happens is when I double this mass, when I double this mass here, and I'm putting a 2 here to double that 0.998, I get this number right here, and it is not twice that number. So something is definitely wrong. You just can't add your final velocities together. You have to do some other method. And the method I came up with is right here. I took the square of each mass. I squared the 2.885 times 10 to the minus fifth. I knocked off 10 to the minus 5 on both of them just to make my numbers easier. And the formula I came up with is velocity equals the square root of v1 squared plus v2 squared to the n, just like c squared equals a squared plus b squared. And the easier math was to leave the v squared as is and add up v1 squared, v2 squared, v3 squared. So doing that, I got rid of a small problem. The next step after doing a solar system was to do a galaxy with everything spread out sort of even. And what I found out on that one is that instead of 2.885, I come up with 2.041, which is smaller. So spreading out the mass doesn't necessarily help me. Now on this model here, I spread out the mass in 5 places, and I did V1, V2, V3, and V4. The last one here, that is my object spinning around, and its mass is not a part of this equation. So the object that has the velocity, its mass does not matter. So what I get on that is 2.635, which is still smaller. And I did one more. Here, and broke this one up into 17, which gives me 16 masses to add up. Did all the numbers on that. If you want to check it out, go for it. And I came up with 3.642. and that is actually quite a bit bigger. But I didn't stop there because my numbers weren't really what I was wanting them to be. As we spread out mass here, we also spread it out circular. And as we bring things out, it makes things quite a bit smaller. And to show you on that one, I did a one with 4 masses just to make it 5 points, like I did on this one here with 1, 2, 3, 4, and 5 points linearly. This one I'm doing in a circle with 4 points in a circle. And I had to come up with forces in this direction. And I came up with that on those. So this is my math, and I came up with 2.042, which is again quite a bit smaller. So as soon as we spread things out, that linear aspect doesn't really work anymore. The next thing I did is I traced out a galaxy. I had a picture of a galaxy on my computer screen. I put a piece of paper up to it, and I traced out some basic lines. And what I'm seeing is the black hole laying flat so that the jets actually go out to this part, push out mass, and push all the mass into one area. And as it grows, it creates a big old long chain this direction. So you have most of the mass in these arms. And the things that make up the mass that a lot of people are trying to contribute to dark matter are black holes, brown dwarfs, wayward planets, planetoids, asteroids, space dust. I don't consider virtual particles to have any make or matter on this. I could be wrong on that one, but I'm not giving it any real credibility. And those pretty much create the chain, the mass that holds the mass that holds this chain together. Once we get out to the end here, top end speed of binary stars. So when you have binary stars going around, that increases the velocity of the light that's coming at us. And when they're looking at these things through telescopes and separating the visible lines to determine the elements, what happens is they're looking at the fastest ones. So binary stars could have some extra on that. They will not make this 3 times faster. It'll just be a small addition to it. So making a better one, a better model of gravity chain, I put this up on a computer screen and I mapped it all out the best I could. What I saw a lot of interesting things on it. Anytime there was a big mass here, you could see holes in it, and there was usually a big blob or big mass in that big hole. There was usually some masses over here where the gravity from this was actually separating the heavier elements from the lighter ones, and the lighter elements going this way, and they were being split. And there's a lot of really neat things going on here if you're looking at mechanics of galaxies. So what I did from here, getting back to the subject, I took my center of mass here, I came out to here, and I took a set of calipers and I just started marking off distances, as equal distance as I could get it, just rough estimate, for each one of these. And I counted up that there were 64, I counted up 64 lines, and I figure I'm starting with 1,000 grams, 936 kilograms, and from there get a nice average, because a chain does just that. It binds together, it holds together. So whatever the speed of this star here is going to have approximately the same speed of the star on the outside. So the closer it is to the gravitational body, the faster it's moving. And you have enough mass in here to hold all these things together, and when you get out here, it creates a giant whip. So the outside pieces are just being whipped around, not by the gravity from what's going in. Excuse me. It's being whipped around this way, not by the gravity forces applying this way, but by another gravity force. Force equals, okay, I guess I have to admit that I'm equation junkie because I had this posted on my wall. Force equals gravitation times mass 1 times mass 2 over r squared. Now what this r squared does is it says that the draw between this mass and this mass, the closer you get to it, the more those forces draw them together and the more they bind to themselves. So this mass here, being very far away, has very little force on it. This mass in the center, even though it is quite massive, it is also very, very far away, and forces do work under r squared. The outside radius was was my last one counted, 0927 meters, and gravitational constant times inside mass. So the expected speed on this would be, on this model, would be 2.6 times 10 to the minus 5 meters per second. Now, if we're looking for 10 times the mass, then we're also looking for the square root of 10 of the speed. If we're looking for 4 to 5 times the mass, which a lot of galaxies have, some 4, some 5, some 10, all of them are a little bit different. That's something that's not really talked about very much on this dark matter problem that everybody's been working on. And the devil's in the details. It really is. And it shows when you stop everything, when you freeze frame. And you look at everything from a point-to-point static form. And that's pretty much what I did. So at 4.5, we're looking at 5.5 times 10 to the minus 5th meters per second instead of 2.6 for the outside. So if we're just using the solar system equation, we don't quite get that 5.5 or anything close to it. Now, with that short chain that I used a very small galaxy, because as the galaxies get bigger, they cloud up, and the visible light really can't see them. You need better spectral lines, better equipment than what I had to actually pick those apart. So using a small one, I was able to bring up the average speed to 3.49 times 10 to the minus 5th seconds, which is almost that 4. So if you're looking at it from the point of view that if a galaxy, when you're looking at the speed of the galaxy, you're looking at the galaxy in this direction. When you're looking at what a galaxy looks like, you have to look at the galaxy in this direction as it spins around, or it spins around the other way. And we're looking at the speed of the outside tip. Now when they're big, they're all clouded up and you can't really easily see them, or I couldn't. So I had to go with a smaller one, which means I'm going to get smaller numbers. And I did. And as far as I'm concerned, this right here is proof that dark matter isn't getting the math wrong. The problem with dark matter, and the reason why people are seeing dark matter, is that we didn't have the math, and the math wasn't there. You have to stop it. You have to look at your vector velocities and your vector forces. And when you do that, dark matter disappears. And I would like to point out one other thing before I go, and you notice that I'm using an ink pen, not a pencil. See you on the next video.